Hello everyone. Hi. Okay. Here, today we are going to study section 9.2, estimating population mean. In other words, we are going to have just a sample mean, and from here we are going to estimate. Okay? We are going to estimate this population, big population mean, which is mu. Okay, so how we are going to do that? And to do that, of course, estimating means we cannot pinpoint that population mean. So we are going to make an interval. Okay, we call that confidence interval. Well, so this is what we did the last time. We estimated the population proportion p, and we started from this known statistic p hat for sample proportion, and then plus minus z sub alpha over 2, and over here what 100 times 1 minus alpha, okay, percent, that is a confidence, level of confidence. Okay, so level of confidence is, for example, 90%. That means this portion has to be 0.9, so alpha has going to be 0.1, like that. And this one times this. Well, I did not write it properly on purpose. So what is this? So z sub alpha over 2, we call this a critical value. And this portion, all together, we call this margin of error. A margin of error. So we are going to put just E, capital E. Excuse me. What is wrong in this formula? Yes, we are estimating population proportion P. So how can you use P? So what do you have to do? Yes, we are going to use what we have. So this part has to be P hat. Sorry. So, estimating population mean, I want to copy this. What's the big deal? So this is my plan. Okay, whether you tell me that it's going to be correct or not, but I'm going to start with the population mean. So we have a sample mean of x bar. So plus minus z sub alpha over 2, we keep the same language of confidence level, things like that. So this time it is going to be like, instead of standard deviation of this sampling distribution of sample proportion, we are going to use sampling distribution of means, okay, sample means. So I'm going to have a sigma over square root of n. I realize it's not going to work. Number one, because mu is unknown to us, therefore what? This sigma also unknown. Sigma also unknown, so therefore we cannot use that. And then your plan changes to, well, what about then sample standard deviation S over square root of n, and then something is not right. We cannot do it this way. Okay, it's not me. I discovered it for the first time. Okay, somebody else discovered it. Okay, so I'm going to propose this problem over here. Earlier in chapter 3, the definition of a sigma was square root of sigma, the little sigma standard deviation is xi minus mu squared over n. On the other hand, the sample standard deviation S is square root of sigma of xi minus x bar squared over n minus 1. There is a discrepancy between n and n minus 1. Alright. So that's why it's not going to work. Okay, we cannot copy this way. So it's not going to work. So who discovered that part first is, his name is William Gossett. William Gossett. He's an Englishman, and he worked for brewing company that's called the Guinness. Yeah, I'm sure some of you heard about it, Guinness, okay, lager. Well, he was working for Guinness, and his job was finding the optimal kind of barley for their flavor, okay? And he experimented, and then for some reason he wanted to find the population mean, and he doesn't seem to find the correct one. So here is the problem. He realized that, there is difference between n and n minus 1 that creates that z is not going to be available. Okay? So William Gossett wrote a paper on that. But when he published the paper, he didn't use his real name. Okay? His real name, because I think that there was a rumor, or could be a fact, but the brewing company did not, of course, they want to have their, trade secret. Okay, so they didn't want to publish anything. Therefore, he had to use pseudonym for his publishing paper. So then he used the word student instead of his last name Gossett. That's why we are going to see student distribution on the bottom of page 112. Okay? Yes. So when you hear student T distribution instead of Z distribution, that means we are estimating population mean middle. Okay? So this one doesn't work. I'm going to erase this. Then what is going to work? So he created a student T distribution. This is a paper I sent you over here. Okay. So compared to Z distribution we use so far, what's the difference? Z distribution is, for example, it's going to show the area. Okay, if you have a Z value over here, the area is going to be to the left. Okay, so that was the associated. But when you have a T distribution, well, it's going to go to the right. Okay, go to the right. So in some sense, it's a more effective one. But T distribution is only for this purpose, no other purposes. You know what I mean? No empirical rule or no other normal distribution stuff. We do not use it. So just go to this area. This is going to be the T value. On top of that, what we have to do over here is, earlier I said the difference between square root of sigma of this xi minus mu squared over n versus square root of sigma of xi minus x bar squared over n minus 1. There is a discrepancy like this. Therefore, we are going to incorporate this n minus 1 into our calculation, but not over here. So when you look at the table, and this n minus 1 is referred to as degrees of freedom. I know it's degrees of freedom. Doesn't sound like a statistics term, right? Okay. So degrees of term. I'm sorry, my printer is making some noises every now and then. Degrees of freedom. So you have to go. Before you go to get into this T distribution, you are going to find the correct n minus 1, not n, n minus 1 is degrees of freedom, and go from here and then find the area over this area, and then you can find the T value. Okay? So we are going to see that soon. So what is this T distribution? T distribution is very similar to Z distribution, but there is a little bit of a difference. Okay, this one versus standard normal distribution, so Z distribution. First of all, the curve is the same. So let's say this is standard normal curve, okay? Standard normal curve. So in other words, this is a distribution of Z. And right in the middle, you have 0, and the sigma is 1. So go to -1, +2, -2, things like that. And the area under the curve is 1, total area is 1, and that is exactly symmetric about this right in the middle, mu. Okay, mu is 0 when it's standardized. Okay, so when you have this, compared to this T distribution is going to be a little under, okay, little under, but the same thing as like a same area. Therefore, what do you have to do? The end part is going to be wider like this, going above, and in the middle is a little lower than standard normal curve. And this the same thing, the total area is going to be 1. Okay, so a little lower, but it's going to be spread a little thicker. Okay, this is T distribution. T distribution, and this T distribution comes with degrees of freedom. Comes with degrees of freedom. Therefore, it's not just one single curve. It's a series of curves. So, for example, degrees of freedom 10, degrees of freedom is 20 or 5. They are going to have a little bit different curve. Okay, slightly different. So, the n is larger. As n increases, the sample size n increases. Sample size n increases. That means it is going to be closer to Z distribution. Okay? So if I give one more, so let's say this is a less sample size, that means going over here is going to be a little more thicker. Like this. Okay? So sample size is getting larger, the curve is getting closer to Z distribution. So between this blue and red T curve, yes, this red T curve has a larger sample size than this. Okay? Alright. So we are going to use just as we did with the Z distribution, but don't forget, always we think about degrees of freedom. Alright, so this T distribution, this T means this. X bar minus mu over S over square root of n. It's very complicated versus what was Z variable. Z value was X minus mu over sigma. It's simple, correct? Okay. On the other hand, this one, here is X bar. So here is X bar minus mu over sigma over square root of n. Not just sigma, but here is S is what? Standard deviation of the sample. Alright, so it looks more complicated. Alright, here we go. Before you go to constructing confidence interval, let's go to example 9.21. Well, here we go. Find the T critical value. T critical value is, earlier we said, the margin of error was what? T sub alpha over 2 times square root of root of, instead of sigma, you are going to have s square root of n. Okay? I'm sorry, not just the whole thing. S square root of n. Yeah, that part is going to be the 1. And 9.21. So that is t critical value such that the area under the t distribution to the right of the t critical value is 0.1. So you go to t distribution and we want to find the t value. The area of the region right to this value is 0.1. Okay? Assuming 15 degrees of freedom. Assuming 15 degrees of freedom. So that is df. Okay. So what do? We are going to do over here, go to this table. First, go to n degrees of freedom is 15. Yes, go to 15 and then go to here. Yeah, just according to this table, 0.1. So go to 0.1, showing this column. So that is 1.341. So this t value turns out to be 1.341. Okay? So go to degrees of freedom. You pick the correct row and then move the column until you see 0.1. That is 1.341. Okay. Well, can you do this one with the calculator? Yes. With the calculator. Yes. What we do is second bars. We use many times. Second bars and then go to menu, invert t. Okay? We want to find the z variable and then we go to a invert norm. Okay, invert norm. So this time is t variable, okay, t value, therefore we are going to do invert t. Okay. Go to second bars and then go to all the way down and find the invert t and then area is 0.1 and df is 15. Oh, I just realized, okay, area, even though, oh yeah, okay, this is what happens. When you use the table, yes, it's going to give you straightforward 1.341. When you use a calculator, yes, when you use a calculator gives you the area to the left. Calculator area gives to the left, therefore this is 0.1, so this portion has to be 0.9. Yes, all right. There are many things you have to coordinate together over here. So this part is a little bit more complicated than this z, okay? Well, so this is 0.9, so you enter area 0.9 and the degrees of freedom, df is 15, and enter, you are going to get 1.34, okay? When you do this, 1.3406, so 1.341. Yes, this one is by hand, by table, and this one is by calculator. Okay, so this is just a simple warm-up, and now we go for a confidence interval. So confidence interval for mu. Population mean. Okay, so what do we have to do? Yes, this portion, yeah, this is error of margin. So what do we have? From our sample, we have the sample mean of x bar. So from here, we are going to extrapolate this one as to the mu, correct? Okay, so in order to do that, just simply we can make an interval for mu. So mu is, okay, for mu, that is x bar. We are going to give an interval, get buffer, okay, plus or minus. What do we do? T sub alpha over 2, as we did this z sub alpha over 2. So T sub alpha over 2, and then of course we are going to consider the degrees of freedom all the time. And then times what? Times square root of, oh sorry, not square root of s over square root of n. Okay? So this part is going to be the error of, margin of error. Alright. So, and what about this? Is going to be a normal distribution. Yes, this normal, in order to have this normal distribution of x bar, what do we have to do? If the population is known for having normal distribution, or what? We do not know the normal distribution of population, but this little n is roughly greater than y equal to 30, and then we can think about normal distribution of x bar. Okay, so we can go from there. And as before, we did this in order to have like a independence of this sample, or those samples. So we are going to have a little n is less than or equal to 5% of population size. Okay, we are going to still check that part. So let's go to example 9.22. Yes, this one we did for the population proportion also. But for this normal distribution, yes, we are going to think these two. Okay? The website fueleconomy.gov allows driver to report the miles per gallon of their vehicle. Okay, so here is miles per gallon, miles per gallon. Oftentimes we say MPG. Okay, MPG here is for 2011 Ford Focus automobiles for 16 and equals 16, and we have values over here. So one person reported that, well, that person got 35.7 miles per gallon, 37.2 miles per gallon, 34.1, and 38.9, dot, dot. Here is 32.2, 40.9, 37.0, and 36.0.